next topic of our kinetics has this interest concentration and chemical rate. We realize that most chemical reactions are indeed reversible. If I think about the collision theory, initially at time 0, I only have reactants involved. There is no product yet made. So only the collisions that are occurring are from reactants. But as time goes by and products are being made, they can indeed collide with one another. And if the orientation in space and with enough kinetic energy, they can break bonds and form new bonds going back to the original reactants. When we say that reactions are reversible, we're simply reminding ourselves that if A plus B collides to make AB compounds can collide with one another and break those bonds. At time 0, the initial concentrations, we only have reactants going on. There are no products yet. And so the earlier the reaction rate is measured, the more dependent those rates are on the initial amounts of reactants. If I let too much time go by, I start to interfere with the rate of the reaction by actually measuring a reverse process. So we call this the initial rate method. This method, called initial rate method, measures the concentrations at time 0 of the reactants as soon as they're mixed. If we know the concentrations of the initial amount of reactants and measure them several times at varied concentrations, we start to get insight with how the concentration is affecting the rate. So this method, called reaction rate method, initial rate method, measures the concentration several different times. So we run probably 2, 3, sometimes 4 different experiments by varying the initial concentrations of reactants. And we start to generate data tables. If I start with 0.1 molar of a reactant, how fast does it go? If I double the concentration, what have I done to the reaction rate? Those initial concentrations of the reactants then get varied, and we start to generate a data table that measures concentration versus reaction rate. So literally our labs have it with a stopwatch. You pour the 2 solutions together, click the stopwatch. How long does it take to see evidence of the product? You'll run the trial again, varying the concentrations, and hit the stopwatch again. By varying the concentrations and running the reaction several times, we start to generate data. But it's very important that we measure at time 0 so that we eliminate the reverse reaction effect. When we start determining rate laws, remember the last page we wrote rate expressions. This is very different. Rate laws show how the rate depends on the concentrations of the reactants. It does not, I'll repeat, it does not have anything to do with the stoichiometry. The rate expression, that's what we just practiced in the previous lesson. That uses the stoichiometry where we use those fractions. Rate laws do not depend upon stoichiometry. They have to be determined via experiment. They have to be based on initial concentrations and reaction speed or kinetics. So the only way to determine a rate law is not from the balanced equation, but from experimental data. If this reaction, and again we wrote that up above if it looks familiar, dinitrogen pentoxide decomposed into 4 molecules of NO2 and 1 molecule of O2. If the reverse reaction does not play a role, notice it's only a forward arrow. You can find the rate will only depend upon the concentration of the reactants. So we write what's called a rate law. The rate is equal to K, which will be the rate law constant, times the concentration of N2O5, notice that's the reactant, raised to some power we do not know. I'll just make up a letter called n. It is not squared. It has nothing to do with the coefficient. It has to be experimentally determined, and I'll explain how. This is called a rate law. Rate is equal to K, a constant, times the concentration of our reactant raised to some power n. The K is a rate law constant. It depends on temperature and the solvent used. And n is called the order of the reactant. It's usually a positive integer. And for the scope of this class, we'll talk about first order and second order. I might comment on a zero order. I have seen that appear in the AP exam, but they're rare. So typically, we're going to look at first order and second order reactions in terms of homework and testing. Rate is equal to K, that's a rate constant, times the concentration of our reactant, N2O5. We do not consider the product in an initial rate method. There is no product at time zero. And N represents an integer called a rate law order. The order with respect, the concentration affects the rate. Let's look at that a little further. If the rate is twice the concentration as the rate was the first concentration, what must be the order with respect to the reactant? I'm missing a slide here. I'm going to pause and pull out the actual PowerPoint slide that's going to give us data. So I'm going to pause the video. You do the same. Give me a moment.